All right, so today we're talking about electrolytic cells, a non-spontaneous electrochemical cell. And I'm going to demo two of these. I have these movies in my webpage, but we're going to try to do these live and in person, best that we can. And I'm going to ask you to take some notes here, okay, to better understand these two type of applications, okay? All right, so now we're doing electrolysis of a fused salt, okay? Or at least we're going to do this as an application. The first thing that you see in any electrolytic type of cell is you're going to see a power supply. You're going to see a battery, because this does not occur on its own. We're forcing redox reactions that don't normally occur to occur, and that's important, okay? So we need to be able to figure out who the anode, the cathode, the flow of electrons, and understand what's happening at these electrodes. Why that's happening is beyond me. Okay, so now, normally we take a salt, which is Ki, okay? And Ki, like all salts, all right, is really a K plus, attracting I negative, who attracts a what? Another I negative, who attracts a K plus, and this is a salt. Okay, it's important you realize that. These ions aren't free. I can make these ions free, okay, by heating them. And so normally electrolysis is done by heating this salt so that these ions can have the energy to pull away from these electrostatic attractions, okay? So today I'm not doing that. I don't have molten, liquefied Ki salt, okay? And again, when you hear of salt or ionic compounds, you got to think that arrangement, okay? So I'm using aqueous, an aqueous solution. So I have free ions by just dissolving. It's not the same, okay, as we would do in industry, but it'll work just the same. So I'm going to get rid of this. So the bottom line is, by having Ki aqueous, okay, in my solution, I want you to write this, okay? So in the beaker, okay, you've got K plus ions, and you have iodine ions. Okay, they're not molten, they're dissolved, which means there's water in there and there's some side reactions I'll talk about at a later date. But we're going to pretend that these are molten. It'll still work, okay? The electrolysis will still work. Okay, now the first step is to understand what's happening here in the battery. Okay, so in the battery, I know you can't see it, but this is a red lead. That's red, and I know I wrote with blue color. And red leads are written for the cathode. So right here, party people, and I could do it right now. Okay, right here is the positive cathode of the battery. Right there, that's that red lead. This black lead here is the anode of the battery. You have to know that. But if I give you positives or negatives, you should be able to handle that. That's negative, right there, okay? So in a battery, voltaic cell, galvanic cell, hey, that's oxidation. Oxidation means LEO, losing electrons. That is producing electrons. Hey, at the cathode of the battery, there's reduction. That's accepting electrons. Electrons flow from the anode to the cathode, except we're not going from the anode to the cathode directly. We're going to have it through a circuit. So the battery is going to force charge to go. So let's start with the anode. What's the anode do? In a battery, it oxidizes and pushes electrons. So it's going to push electrons in this direction. And electrons always flow from the what to the what? Anode to the cathode. So this guy right here must be the cathode, because we have electrons moving toward it. And I'll just draw it up close and personal. Hey, there's negative electrons there. And it's hard to do that because I'm so up close and personal with it. But there's negative charges, which are electrons. Let's put negatives here. And this is still the cathode. So to explain this, I have an exposed piece of metal. We're pumping electrons. and we're making this metal negative. This is a conductor. I'm sorry, the metal's a conductor, and this is an insulator. Okay, so we're exposing the negative here. So party people, the cathode is what charge? I'm pumping negatives to it. It's got to be negative. The cathode is negative. Who is making it negative? Who is responsible? The battery's anode. It is pumping electrons. It's making it negative. I was to clip this, it wouldn't be negative anymore. Okay? Now let's look at the other way. The cathode of the battery. The anode is pumping electrons. The cathode is pulling electrons. It's giving energy here. So this guy is doing what? Pulling electrons toward it. The action of pushing charge and pulling charge is the energy that's going to make this happen. So electrons are being what? Electrons are being pulled away from this electrode, which must be the what then? The anode of the electrolytic cell. Now, and of course, check it out, electrons always flow from the anode to the cathode. Always from the anode to the cathode. That stays the same. But in the case of electrolytic cell, because we're pulling charge this way, this guy is going to be positive. We label it positive to show that, hey, electrons are flowing from this. By the way, don't forget that these tips are also positive. And you can think of this tip as also, okay, the anode and the cathode, because they're connected. But there's positives here. Now, why is there really positives? Because we're oxidizing, we're pulling electrons away. This is losing electrons, hey, positive. This is I'm pumping electrons. The battery is making the charges happen. Clip the leads, turn off the battery, nothing happens. Okay, so what's going to happen now? Okay, well, party people, I'm going to turn this on. This gets negative, this gets positive. Well, who's going to be attracted to who? Makes sense, logical. Make this logical for yourself. Isn't the positive ion going to be attracted to the negative electrode? Well, that's how it works. See, if you can start understanding this, not memorizing it, then it's with you. It's never going to leave you. Just use your logic. Positives go to negatives. And this negative is going to be attracted to this positive. So at this electrode, the place of redox is where the redox reaction is going to occur. So the K plus comes to the cathode. All right, now let's go to here. The K plus. Now wait a minute. What's the K plus going to do? What happens at a cathode? What always happens at a cathode? Red cat. Reduction. What's going to happen is the K plus is going to what? Yeah, it's going to gain an electron. And what's it going to become? What charge? Right, and what is the phase of a pure metal? Solid. We're going to go from aqueous ion that's dissolved to a solid metal. And anytime we see aqueous to solid, that's plating. We expect plating, pure metal, to occur, at the cathode. Just like the voltaic cell. Remember the copper plus 2 in the Daniell cell? Gaining 2 electrons, it was getting bigger. So I expect that to happen. So let's go down here. Reduction. We've got K plus in solution. It's being forced electron onto it, and it's becoming K0. All right? The net potential. Okay, the net potential. Looking at my standard reduction potential chart for potassium. Okay, K plus an electron as written is negative 2.92. Negative 2.92. What does it speak to you? For that to happen, why is that so negative? I don't mean to be a downer, but why is that so negative? Because K0 loves to what? Oxidize so well, it hates to go the other way. So party people, we're We're making it happen, okay? Okay, good. Over here, what's happening here? Well, I negative, I'll write the half reaction to the left. I negative is, occurring at the what? At the anode, anox. I negative is attracted to the positive anode because electrons are being pulled away, and it's going to be forced to oxidize. Leo the lion. So oxidation, okay, oxidation occurs there. So it loses an electron and becomes what? I0. Now, anytime, we should know who our diatomic elements are. There's a mnemonic, Hofbrinkel's. H2, O2, F2, Br2, I2, N2, Cl2. These love to bond with themselves. So iodine loves the Christmas. Iodine, what just happened? What just happened? How do I get this back? Start. Okay, got it. So iodine likes to become I2, which means I need what? 2 of these, right? I multiply everything by 2. That's really the half reaction, because it loves to be a diatomic element. Okay, so party people, let's put this down here. The oxidation that occurs at the anode, anox. Oxidation always occurs at the anode. Okay, no matter if it's the redox or whether it's the electrolytic cell or the voltaic cell. And so what do I have? 2 of these iodine ions plus, Christmas. I'm oxidizing. Yep, because I'm oxidizing. And that's a good point. You're never going to have electrons on both half reactions, right? So 2 iodine negatives in solution are going to go to give off 2 electrons and become I2, which by the way is 0. Very simple. Okay? Now what's the net potential for iodine? Okay, I negatives. I negatives hate to oxidize. So it's going to be negative 0.53. I've got to flip it around. So both don't like to occur. There's no pathway. All right, let's find the overall reaction. Well, that's easy. Hey, I got 1 electron here. I got 2 electrons here. I have to balance my charge. You guys are not doing it in your quizzes. So I got to multiply by the distributive property, times this by 2. This makes this 2 and this 2. And now I have 2 electrons that I can cancel. Add them together. What do I get? 2K plus 2 iodine negative gives me 2K0 plus I2. Don't write electrons. If you want to make sure you did this right, check your charges. 2 times plus 1, plus 2. 2 times negative 1, negative 2. Negative 2 and a plus 2, 0. This side is 0. Always do a quick check. Let's do the net potentials. E0 cell. Add them together, both negative. 5. 9 and 5 is 14, carry the 1. Negative 0.345 volts, should put a unit there. What's that mean? For this to occur, I need that much free energy to force it to happen. I'm going against nature. Look at this negative sign. This wants to go this way. This one wants to go what? The other way. They both want to do the opposite. We're forcing it to occur by adding that voltage, that negative, large negative, is making me do that. Okay, so what are we doing here? Real quickly, same idea. Okay, black Christmas. I got these. I would have just make sure I got the black lead with the black lead. So here we go. In my demonstration here, let's do it. It's set up the same way. Okay, so I've got the red lead here, which is my anode. Why is it my anode? Because it's connected to the cathode of the battery. Okay, the cathode's positive, so it makes this guy positive. Hey, this is connected to my anode, the black lead here, which is negative, so it makes this negative. Anode goes to the cathode. Okay, and anode flows to the cathode. This is negative, this is positive. Okay, what am I going to make on the left-hand side? Pure iodine, which has a color. What am I making on the right-hand side? Pure potassium. But pure potassium is very reactive, right? So pure potassium explodes in water. So as soon as I make some pure potassium in this aqueous environment, it's not really molten, okay? What's going to happen is the pure potassium is going to make a gas. Anyone know what that's going to be? Lab 1, conclusion. Magnesium is not nearly as reactive as potassium. Potassium is a big element. It's going to push its electrons on the water. Who is electron deficient in water? Hydrogens. The hydrogens are going to accept the electrons and become hydrogen gas. So we should see some fizzing going on here. You're not going to see the plating of the metal here because the metal is too reactive. But you can buy pure potassium. It's dangerous. It's explosive. You can't find pure potassium in the ground because it's already reacted into something else. So how do they have pure potassium? They do this with a molten salt, not with water. Okay? I have pure sodium in the back room. How do I have pure sodium? It's also more reactive. They take the salt or the ore of it and they do electrolysis. A quick story. When they made the Washington Monument for George Washington, they wanted to pick for the spire, the top piece of the monument. They wanted to pick the most expensive metal. Okay? So they picked aluminum. At the time, aluminum was the most precious and rarest metal there was. It was the most expensive metal. A few years later, they discovered this process. And they took what? Aluminum oxide, or aluminum ore. Aluminum that's already been reacted. They heated it, melted it, put 2 electrons in. The aluminum plus 3 went to the what? Cathode, became pure aluminum. That's how they purify metals. We purify ores. Ores are the metals we find in the ground that have reacted already. This is how we purify them. All right? And it's cheaper today to purify aluminum than to recycle. It's part of the problem. So who cares? Let's turn this on. So nothing is occurring because it's a non-spontaneous process. It's not going to occur unless I force it to happen. That's what the battery's doing. Okay? So turn it on. And I don't know if you see it, but you got some fizzing right here, which is the hydrogen, and here is the aluminum. I'm sorry, here is the iodine. I said aluminum. Okay? Okay, so if I get up close and personal with it, you can see the fizzing to the right. That's hydrogen gas as the what? Potassium becomes a metal. And then you can see the iodine. Okay, it's got a distinct color being made there. Now, if this was molten salt, I can make the pure compounds. Here we've got reactions with water. Okay, but you just get the idea. Okay, so that's done, maybe. Let's start this again. Okay, and stop this and go on to the next one. Okay, oh, shocked myself. All right. So the next one, flip the page over 9 times. Here we're going to do lead nitrate here. Hold on to your ponies. Let me get some, another, just an aqueous solution here. I know that I brought it over somewhere. Okay. I thought I had some made. I thought I did too. Just give me a second. We're going to be ready to rock and roll in a second, and I thought I had some made. Oh, come on, Rosie. Whatever. Okay. Okay. So I've got kind of a weird scenario here for my electroplating. Okay. As I'm going to try to plate, okay, one metal onto itself. We'd actually never do that, but this is a good little demonstration. I'm fresh out of gold, so I have a tough time gold plating something. Years ago, I could do this demo and gold plate a little bit. All right. And that's good enough, I think. Yeah, we'll make that work. Okay, so let's connect some leads and go on to the next one. And now this is another electrolytic cell. You can see nothing is occurring because I need battery to make it happen. So I need battery. Okay, so here it is in all of its glory. Hey, same picture. The power source is a little different. I apologize, but not really. Okay, so I'm going to put the red lead, which is from my cathode of the battery, to the left. And make my black lead to the right. Okay. All right, cool beans. Now what am I doing here? Well, I'm going to try to plate lead with lead. These are 2 lead electrodes. And let's talk about what we're doing here. Okay, so same idea. There's my red lead right down here. So this is my red lead.
Is the red lead always the cathode?
Usually, by convention, people use the red to remind yourself, hey, put that on the cathode. Can it work without it? Of course. It's just basic copper wire with a red insulator. But it just helps us remember, hey, I'm going to connect it to the cathode. So that's a red little cathode here. And the cathode of the voltaic cell is what? What's its charge? Positive, because that's the place where reduction occurs or electrons go to in the battery. Here, the black lead, okay, is attached to the anode of the battery. We know the anode of the battery is negative. We make it negative by convention because, well, because that's the place where electrons come out of. Okay, so let's start with the black lead. Electrons are being pumped from the battery, okay, to this electrode here. And so electrons are being built up here. Electrons flow from the anode to the cathode. That's the cathode, always. We're making that the cathode because we are attaching this metal to the negative lead or the negative part of the battery, the anode. And so, by us pumping electrons here, what charge does the cathode become? Negative, correct. All right. Going back to the battery, because it's the battery that makes it happen. I've got this red positive lead, which is the cathode. Cathodes pull charge toward it. So I'm pulling charge toward it. So that charge is coming from this part of the electrolytic cell. So if this is the cathode of the battery, electrons flow from the anode to the cathode always. So there's your anode. Now, the battery's anode makes the cathode negative, so therefore the cathode that's positive makes the anode positive. Or, because we're losing electrons from this part of the system, it makes this positive. I don't care how you want to think about it, but you're going to have some positives here as we take electrons away. And on this side, you're making this negative cathode, positive anode. Who makes it? The battery. Okay, now, let's think about this for a second. How does this start? Well, lead, right here, likes to oxidize, somewhat. So here's the oxidation. Anox, red cat, another thing that works always. Oxidation is always at the anode, battery or not. So same is true here. So take lead 0. It's going to become Pb plus 2 and give off 2 electrons. So a piece of solid what? A piece of solid becomes Pb plus 2. Electrons get shipped and are pulled to the cathode. The cathode is pulling on this. In fact, okay, lead does oxidize on its own a little bit. In fact, its standard reduction potential is positive 0.13. So, Christmas. So positive 0.13 volts. Okay? So it does oxidize a little bit, but this cathode makes it oxidize like 2,000 times more. The pulling action of the battery, okay, really makes this act as if it was a metal that's highly reactive. Okay? Now, what happens to the cathode? Red cat. Red is what? Reduction. So we're going to make solid Pb plus 2 by the metal 0 becoming positive by kicking the electrons or giving them to the cathode. And who's got electrons that are rich in this area? The negative cathode. Why? Because this is attached to the anode that pumps electrons to this cathode. So the Pb plus 2 comes running. Says, thank you very much. And what happens at the cathode always? Red cat. Reduction. Pb plus 2 gains 2 electrons to become Pb0. And you should know something. This is aqueous, or liquid if it was in a molten state. And this is solid. Anytime we have a metal, with the exception of mercury, okay, that's 0, sorry, we're going. So plating is occurring where? At the cathode. Whether it's the voltaic cell, the electrolytic cell, electrolysis, electroplating. It's the only place because the cathode's negative. The positive ion of a metal becomes 0 by gaining 2 electrons. Why 2 electrons and why are they there? Because the anode pumped them there. Okay, so that's important. And by the way, what's the standard reduction potential here? Well, if it was positive 0.13, wouldn't this be negative 0.13 volts? And if you add them together, you get 0. Okay? So, what do we expect to happen? We expect plating, we expect the lead to build up here, and this one to get smaller if I turn it on. How come it's not working right now? Why do I need the battery on? Not spontaneous. I need a power source. I need someone to use energy to make this happen. This doesn't occur by itself. There's no pathway. So let's turn it on. Let's not forget what's happening in this drawing. I know I have it here, but we've got electrons pumped here. This is my cathode because we're putting electrons here, and it's negatively charged. We're sending electrons away because the anode oxidizes and sends electrons away to the cathode. And so this is producing positive Pb plus 2, and that goes there. So, let's turn it on. We expect the plating to occur to the right. And let's just turn it on and force it to happen. And there we go. And so as we turn this on, we're forcing this to oxidize. It's getting smaller. Pb plus 2 is going into solution. And that Pb plus 2 is doing what? Going toward the negative ion. Positive plus 2 is really attracted to these electrons. And it's becoming solid lead. And you can see it growing like a chia pet. Okay? And it's getting bigger. All right? And if you look closely, this is getting smaller. This is dissolving solid to what? Plus 2, sending electrons back to the circuit. And here we have lead plus 2. Now, this isn't perfect plating. You wouldn't actually plate this way in commercial because you wouldn't use water. As soon as you make a zero charge substance, it repels water. Water is polar. Something zero, water can't dissolve. So this is not the best way to plate, but we're getting lead, solid lead appearing on that. And it's growing, getting bigger. Plating occurs at the cathode. Why? Because that's the place where you have reduction. That's the place where you're going to gain charge from a metal ion who's free to become solid metal. This occurs at the cathode in electrolysis, electroplating, and in voltaic cell, always. Okay? Now, let's get up close and personal and see what we got here. That's clearly getting bigger. And if you go over here, I don't know if you can see it, it's starting to get etched, irregular shaped, as it's getting smaller. Hard to see something getting smaller, but that sucker is growing. Okay, now I'm almost done. I'm going to stop this and show you about the spontaneity. What drives the system is the battery. The battery gives the cathode anode charges. The reason why it did what? It plated to the right is because I made the right electrode the what? I decided to put the anode to this one. I decided that this was the cathode. Just by, well, what if I want to make this the cathode? What do I got to do? Switch the leads. So I'm not going to do it on top. I'm going to do them by the battery. So I'm going to switch the leads. So I'm going to switch what was the anode to the cathode down here. Okay? Now I'm going to turn it on. What do I expect to happen? Now, this is the cathode because now I switched it to the anode. And what's happening? The Pb plus 2 is now what? Going and becoming pure lead here. And this should be what? Dissolving and getting smaller. And so you can see it's getting bigger, okay? And that one should eventually fall off. Now if I go to lunch for 15 to 20 minutes, okay, this entire electrode will go missing. I'll just, wherever it's not touching the water, you'll see it, the rest of it's in solution. This would be a big mess. So if you look carefully at close and personal, you'll see the one to the right dissolving. You can see it kind of dissolving, can't you? Falling off. And this one saying, yes. All right, because we decided what was going to be the anode and what was going to be the cathode. All right, and so you don't have an electrolytic cell without a battery. Notice there's no what? Salt bridge. No salt bridge whatsoever. Don't need one. In fact, do we want electrical neutrality? Do we want electrical neutrality? No, we want this to be negative. This to be positive. Notice it's getting kind of what? Do you see how it's getting what? Irregular here as it's losing. Okay, so that's what we did today, okay, in the other class, and that's all we're doing today is I'll walk you through that. Another way to think about electrolytic cells by two good demonstrations. They are limited by the fact they're in water. We don't electroplate electrolysis actually in water solutions, but we still got the same concepts done here, okay? And you're going to extend it to your homework. So that's all we got today.